Alright, so we're still working on example 1. We've calculated what the electric field due to the point charge and the spherical conductor is. We've got the magnitude and direction of both of those fields. And now we need to add those two fields together to determine what the net field is. And when we add vectors together, we have to add them in component form, right? We can't just take the magnitude of these two vectors and add those numbers together. That will not be the magnitude of the net field. For example, if they pointed in opposite directions and had the same magnitude, then the net field would be 0. Right? So we can't just add the magnitudes together. So let me write out the components that we need to add. So this will be the field for the point charge, and then I'll put the field for the sphere over here. So the magnitude of the field for the point charge is this kq over x1 minus x2, and that was squared. So we need to calculate the x component, and we need to calculate the y component. Then for the sphere, the magnitude is related to capital Q in there. And we need to calculate the x and the y components for this as well. So the x and the y components depend on the direction. So for this point charge field, it points straight to the left. So actually the x component we know is going to be negative because it points in the negative x direction here. And the y component is going to be 0 because it doesn't point up or down. So it only points to the left, so we can immediately write down the x component of the field. And it's important that we have this negative sign here. And then the y component of that field is going to be 0. For the sphere, remember that the field is going to point up and to the right towards the sphere. The magnitude of that field is given here. And then it makes some angle with the x-axis, which we have calculated. And so the way that I go about finding the x and the y components for some vector that points in a arbitrary direction is I use trigonometry. So let's just use the triangle, a triangle that includes this angle, and whose hypotenuse is the magnitude of the vector that we are looking for the x and the y components of. Then the length of this side of the triangle, the length of the adjacent side of that triangle is the x component, and the length of the opposite side of that triangle is the y component. So to find the x component of the electric field, I take its magnitude and I multiply by cosine of that angle. And to find the y component, I take its magnitude and I multiply by sine of that angle. So there's the x and the y components for the two fields that we need to add together. And now to add them together, I just add the x components together, and I add the y components together. That'll give me the x and the y components of the net field. Then I'm going to have to figure out what the magnitude of the net field is from those x and y components. Alright, so the net field then, let me say E sub n for net, and this is the x component of the net field. It's going to be kq over x2 plus y2. So this is the x component of the field from the sphere, and then I'm going to add the x component of the field from the point charge, and that has a negative sign in it, so that's why this becomes subtraction here. And then the y component is actually just the y component of the field due to the sphere, right? Because the point charge doesn't have a y component in its field. So this is just going to be kq over x2 plus y2. There we go. So that is the net electric field components. I could write this down as, so the vector that is the net electric field, I could write as the x component times x hat plus the y component times y hat. Now I need to figure out the angle and magnitude, or the direction and magnitude of this vector. So let's draw another picture to see sort of what it is that we've got so far. So this is the field that points towards the sphere. This is the field that points away from the point charge. And I'm going to add those together to give me something that looks like this. So this is the sphere's field, this is the point charge's field, and then this is the net field. So the two things that I want to calculate are the magnitude of that net field and the angle that that net field makes with the positive x-axis. So I need to use Pythagorean theorem to calculate what the magnitude is, and then I need to use some trigonometry to calculate what that angle is. And so there's multiple ways I could use the trigonometry. What I'm going to do, though, in this case is I'm going to draw this triangle here, and I'm going to use this angle. Let me call that phi. I'm going to calculate what that angle is based off of the components of that field, and then I'm going to use that to figure out what the total angle is by adding 90 degrees to it. So let's do the magnitude first. The magnitude of the net field is going to be the x component of the net field squared plus the y component of the net field squared, square root of. So I just need to take the x and the y components that I have calculated, square them, add them, and then take the square root. Okay, so there's x component squared. There's the y component squared. The square root of those added together is going to give me the magnitude. Alright, last thing. Only thing I have left to do is to calculate that angle. So let me draw this triangle that I'm going to use to calculate that angle. Okay. So I'm going to use trig to find out what this angle is, and then I'm going to take that and determine what the angle with respect to the x-axis is. So the length, so what I have drawn here is a triangle that includes some angle. I'll say that the hypotenuse of that triangle is the magnitude of the field. I'm going to have the adjacent side of the triangle, which is the side next to this angle. That will then be the y component of the net field, and then the opposite side is going to be the x component. Whoops. It's going to be the x component of the net field. And so if I look at the trig identities that I have, right, so cosine of that angle is going to be e sub, it's the adjacent over hypotenuse, so this would be net y over net. Sine of that angle would be the opposite over the hypotenuse, so that would be e sub n x over the net. And then tangent of that angle would be e sub n, would be the opposite over the adjacent, so it would be the e sub n x over e sub n y. Now I've got all three of these lengths now. Right, so these two I got from the addition. I got the x and the y components from the when I added them together, and then I just got done calculating what that magnitude is right here. So I also have that magnitude, which means that any three of these would work. I could use any three of these. Now, the one that we typically use when we're doing these direction calculations is that we use the tangent one, and the only reason is because we can calculate that without calculating the magnitude of the vector. So if all I really need is the direction of the vector, I can calculate this direction without having to first calculate the magnitude, as long as I have the x and the y components. So that's what I'm going to do. So tangent of that angle is equal to the ratio of the x component over the y component, which means that that angle is equal to the inverse tangent of that ratio. Alright, and I've got the x and the y components, so this is going to be inverse tangent of there we go. It's going to be inverse tangent of that ratio. and then the angle that I want. So let's say that the, now be careful here because I have an angle drawn, or I have an angle written down here. This is the angle that is associated with the vector, or the field vector, that points towards the sphere. All right, so we're using theta for that angle. What I just calculated was this phi. What I really need is with respect to the x-axis, or I could, I mean, it is perfectly reasonable to just say, or perfectly acceptable to say, that the net field is equal to its magnitude, which I calculated above, and then give a direction and say that it is it is at some angle with respect to the plus y axis. And that angle then is the exact angle that I just calculated. Now, most of the homework problems are going to require us to specify this angle with respect to the plus x-axis. So it's going to be the magnitude that we calculated at that angle plus 90 degrees with respect to the plus x-axis. So there we go. There's the direction and magnitude of the net field. This will give us the direction, and this will give us the magnitude. We can plug in the numbers that were given for the problem, and we can calculate numbers for both of those.